Hi, I'm Fernand Brunschwig. I'm president of STEM Teachers NYC. And I'd like to speak with you today about superposition, the concept of superposition in quantum mechanics, and particularly in quantum computing. Superposition is something that I think we've all heard of in connection with waves. In music, you can have harmonics. You can have a string that plays two notes at once. The string is in a superposition of two different modes of vibration. We can hear several notes at once. Our ear can respond simultaneously to all those different notes. And again, our ear has to be in a superposition of these various modes and these various ways of vibrating. But in quantum mechanics and quantum computing, we're talking about superposition in a similar way, but it's much more powerful and much more interesting than what you find in wave theory. In quantum mechanics, superposition refers to the fact that you have a system that has two different fundamental modes, but that it can be in an infinity of different combinations of those modes. That you can define the fundamental modes within which something can vibrate, but it can then assume many different combinations of those two fundamentals. And that's what I'd like to try to explain a little more clearly today, particularly with regard to the polarization of light. Light can vibrate in basically two different ways. It can vibrate in a vertical mode, or it can vibrate in a horizontal mode, and in any combination of that. This is a good example of the quantum mechanical superposition, where we can think about it in two different ways, and we can analyze it and measure it in two different ways. But the light itself can be in an infinity of different states with respect to those two different modes. Now, to get at this, to think about this clearly, we need to use vectors. And so I just want to quickly review some basic things about vectors. The idea of unit vectors is the idea of a vector that has unit length. We all know about x, y, and z. We're just going to use a two-dimensional plane so that we have quantum systems that can have two different fundamental modes or two different fundamental bases. Now, the unit vectors can be the basis of any vector in the two-dimensional plane. The most popular ones are the I vector, which is a unit vector that points along the x-axis, and the j vector, which is a unit vector of unit length that points along the y-axis. And then any other vector that you have in the entire plane can be written down as a superposition of those two different fundamental components, is what we refer to them in vector analysis. Now, I'm going to turn the camera so that you can see what I'm writing. So just one second.